This sound file contains the spoken word version of a Wikipedia article on the asteroid belt. It is recorded by user S_Whistler, and the material was recorded on the 29th of March 2012. The asteroid belt, from Wikipedia, the free encyclopedia, at en.wikipedia.org. The asteroid belt is the region of the Solar System located roughly between the orbits of the planets Mars and Jupiter. It is occupied by numerous irregularly shaped bodies called asteroids or minor planets. The asteroid belt is also termed the main asteroid belt or main belt because there are other asteroids in the Solar System, such as near-Earth asteroids and Trojan asteroids. About half the mass of the belt is contained in the four largest asteroids: Ceres, 4 Vesta, and 2 Pallas, and 10 Hygiea. These have mean diameters of more than 400 kilometers, while Ceres, the asteroid belt's only identified dwarf planet, is about 950 kilometers in diameter. The remaining bodies range down to the size of a dust particle. The asteroid material is so thinly distributed that numerous unmanned spacecraft have traversed it without incident. Nonetheless, collisions between large asteroids do occur, and these can form an asteroid family whose members have similar orbital characteristics and compositions. Collisions also produce a fine dust that forms a major component of the zodiacal light. Individual asteroids within the asteroid belt are categorized by their spectra, with most falling into 3 basic groups: carbonaceous, silicate, and metal-rich. The asteroid belt formed part of the primordial solar nebula as a group of planetesimals, the smaller precursors of the planets, which in turn formed protoplanets. Between Mars and Jupiter, however, gravitational perturbations from the giant planet imbued the protoplanets with too much orbital energy for them to accrete into a planet. Collisions became too violent, and instead of fusing together, the planetesimals and most of the protoplanets shattered. As a result, most of the asteroid's belt mass has been lost since the formation of the solar system. Some fragments can eventually find their way into the inner solar system, leading to meteorite impacts with the inner planets. Asteroid orbits continue to be appreciably perturbed whenever their period of revolution about the Sun forms an orbital resonance with Jupiter. At these orbital distances, a Kirkwood gap occurs as they are swept into other orbits. Other regions of small solar system bodies include the Centaurs, the Kuiper belt and scattered disk, and the Oort cloud. Contents: History of observation, Origin, Characteristics, Collisions, Families and groups, Exploration. History of observation. In an anonymous footnote to his 1766 translation of Charles Bonnet's Contemplation de la Nature, the astronomer Johann Daniel Titus of Wittenberg noted an apparent pattern in the layout of the planets. If one began a numerical sequence at 0, and then included 3, 6, 12, 24, 48, etc., doubling each time, and added 4 to each number, and then divided by 10, this produced a remarkably close approximation to the radii of the orbits of the known planets as measured in astronomical units. This pattern, now known as the Titus-Bode law, predicted the semi-major axes of the 6 planets of the time: Mercury, Venus, Earth, Mars, Jupiter, and Saturn, provided one allowed for a gap between the orbits of Mars and Jupiter. In his footnote, Titus declared, "But should the Lord Architect have left that space empty? Not at all." In 1768, the astronomer Johann Elert Bode made note of Titus's relationship in his Anleitung zur Kenntnis des bestimmten Himmels, in English, Instruction for the Knowledge of the Starry Heavens, but did not credit Titus until later editions. It became known as Bode's law. When William Herschel discovered Uranus in 1781, the planet's orbit matched the law almost perfectly, leading astronomers to conclude that there had to be a planet between the orbits of Mars and Jupiter. In 1800, the astronomer Baron Franz Xaver von Zach recruited 24 of his fellows into a club called the United Astronomical Society, which he dubbed informally the Lilienthal Society, for its meetings in Lilienthal, a small city near Bremen. Determined to bring the solar system to order, the group became known as the Celestial Police. Notable members included Herschel, the British Astronomer Royal, Neville Maskelyne, Charles Messier, and Henrik Olbers. The society assigned to each astronomer a 15 degrees region of the zodiac to search for the missing planet. Only a few months later, a non-member of the Celestial Police confirmed their expectations. On the 1st of January 1801, Giuseppe Piazzi, chair of astronomy at the University of Palermo, Sicily, found a tiny moving object in an orbit with exactly the radius predicted by the Titan-Bode law. He dubbed it Ceres, after the Roman goddess of the harvest and patron of Sicily. Piazzi initially believed it a comet, but its lack of comma suggested it was a planet. 15 months later, Olbers discovered a second object in the same region, Pallas. Unlike the other known planets, the objects remained points of light even under the highest telescope magnifications, rather than resolving into disks. Apart from their rapid movement, they appeared indistinguishable from stars. Accordingly, in 1802, William Herschel suggested that they be placed into a separate category, named asteroids, after the Greek asteroides, meaning star-like. Upon completing a series of observations of Ceres and Pallas, he concluded, "Neither the appellation of planets nor that of comets can with any propriety of language be given to these two stars. They resemble small stars so much as hardly to be distinguished from them. From this their asteroidal appearance, if I take my name and call them asteroids, reserving for myself, however, the liberty of changing that name, if another, more expressive of their nature, should occur." Despite Herschel's coinage, for several decades it remained common practice to refer to these objects as planets. By 1807, further investigation revealed 2 new objects in the region, 3 Juno and 4 Vesta. The burning of Lilienthal in the Napoleonic Wars brought this first period of discovery to a close, and only in 1845 did astronomers detect another object, 5 Astrea. Shortly thereafter, new objects were found at an accelerating rate, and counting them among the planets became increasingly cumbersome. Eventually, they were dropped from the planet list, as first suggested by Alexander von Humboldt in the early 1850s, and William Herschel's choice of nomenclature, asteroids, gradually came into common use. The discovery of Neptune in 1846 led to the discrediting of the Titus-Bode law in the eyes of scientists, as its orbit was nowhere near the predicted position. To date, there is no scientific explanation for the law, and astronomers' consensus regards it as a coincidence. The expression asteroid belt came into use in the very early 1850s, although it is hard to pinpoint who coined the term. The first English use seems to be in the 1850 translation of Alexander von Humboldt's Cosmos, and the regular appearance, about the 13th of November and the 11th of August, of shooting stars, which probably form part of a belt of asteroids, intersecting the Earth's orbit and moving with planetary velocity. Other early appearances occur in Robert James Mann's A Guide to the Knowledge of the Heavens. The orbits of the asteroids are placed in a wide belt of space. The American astronomer Benjamin Pierce seems to have adopted that terminology and to have been one of its promoters. 100 asteroids had been located by mid-1868, and in 1891 the introduction of astrophotography by Max Wolf accelerated the rate of discovery still further. A total of 1,000 asteroids had been found by 1921, 10,000 by 1981, and 100,000 by 2000. Modern asteroid survey systems now use automated means to locate new minor planets in ever-increasing quantities. Origin. Formation. In 1802, shortly after discovering Pallas, Heinrich Olbers suggested to William Herschel that Ceres and Pallas were fragments of a much larger planet that once occupied the Mars-Jupiter region. This planet, having suffered an internal explosion, or a cometary impact many million years before. Over time, however, this hypothesis has fallen from favor. The large amount of energy that would have been required to destroy a planet, combined with the belt's low combined mass, which is only about 4% of the mass of the Earth's moon, do not support this hypothesis. Furthermore, the significant chemical differences between the asteroids are difficult to explain if they come from the same past. Today, most scientists accept that, rather than fragmenting from a progenitor planet, the asteroids never formed a planet at all. In general, in the solar system, planetary formation is thought to have occurred via a process comparable to the long-standing nebula hypothesis. A cloud of interstellar dust and gas collapsed under the influence of gravity to form a rotating disk of material that then further condensed to form the Sun and the planets. During the first few million years of the solar system's history, an accretion process of sticky collisions caused the clumping of small particles which gradually increased in size. Once the clumps reached sufficient mass, they could draw in other bodies through gravitational attractions and become planetesimals. This gravitational accretion led to the formation of the rocky planets and the gas giants. Planetesimals within the region which would become the asteroid belt were strongly perturbed by Jupiter's gravity to form a planet. Instead, they continued to orbit the Sun as before, while occasionally colliding. In regions where the average velocity of the collisions was too high, the shattering of planetesimals tended to dominate over accretion, preventing the formation of planet-sized bodies. Orbital resonances occurred where the orbital period of an object in the belt formed an integer fraction of the orbital period of Jupiter, perturbing the orbit into a different orbit. The region lying between the orbits of Mars and Jupiter contains many such orbital resonances. As Jupiter migrated inward following its formation, these resonances would have swept across the asteroid belt, dynamically exciting the region's population and increasing their velocities relative to each other. During the history of the solar system, the asteroids melted to some degree, allowing elements within them to be partially or completely differentiated by mass. Some of the progenitor bodies may even have undergone periods of explosive volcanism and formed magma oceans. However, because of the relatively small size of the bodies, the period of melting was necessarily brief compared to the much larger planets, and had generally ended about 4.5 billion years ago, in the first tens of millions of years of formation. In August 2007, a study of zircon crystals in an Antarctic meteorite, believed to have originated from 4 Vesta, suggested that it, and by extension the rest of the asteroid belt, had formed rather quickly, within 10 million years of the solar system's origin. Evolution. The asteroids are not samples of the primordial solar system. They have undergone considerable evolution since their formation, including internal heating, surface melting from impacts, space weathering from radiation, and bombardment by micrometeorites. While some scientists refer to the asteroids as residual planetesimals, other scientists consider them distinct. The current asteroid belt is believed to contain only a small fraction of the mass of the primordial belt. Computer simulations suggest that the original asteroid belt may have contained mass equivalent to the Earth. Primarily because of gravitational perturbations, most of the material was ejected from the belt within about a million years of formation, leaving behind less than 0.1% of the original mass. Since their formation, the size distribution of the asteroid belt has remained relatively stable. There has been no significant increase or decrease in the typical dimensions of the main belt asteroids. The 4:1 orbital resonance with Jupiter at a radius of 2.06 AU can be considered the inner boundary of the asteroid belt. Perturbations by Jupiter send bodies straying there into unstable orbits. Most bodies formed inside the radius of this gap were swept up by Mars or ejected by its gravitational perturbations in the early history of the solar system. The Hungaria asteroids lie closer to the Sun than the 4.1 resonance, but are protected from disruption by their high inclination. When the asteroid belt was first formed, the temperatures at a distance of 2.7 AU from the Sun formed a snow line below the freezing point of water. Planetesimals formed beyond this radius were able to accumulate ice. In 2006, it was announced that a population of comets had been discovered within the asteroid belt beyond the snow line, which may have provided a source of water for Earth's oceans. According to some models, there was insufficient outgassing of water during Earth's formative period to form the oceans, requiring an external source such as a cometary bombardment. Characteristics. Contrary to popular imagery, the asteroid belt is mostly empty. The asteroids are spread over such a large volume that it would be improbable to reach an asteroid without aiming carefully. Nonetheless, hundreds of thousands of asteroids are currently known, and the total number ranges in the millions or more, depending on the lower size cutoff. Over 200 asteroids are known to be larger than 100 kilometers, while a survey in the infrared wavelength shows that the asteroid belt has 700,000 to 1.7 million asteroids with a diameter of 1 kilometer or more. The apparent magnitudes of most of the known asteroids are 11 to 19, with a median at about 16. The total mass of the asteroid belt is estimated to be 2.8 times 10 to the power of 21 to 3.2 times 10 to the power of 21 kilograms, which is just 4% of the mass of the Moon. The four largest objects, Ceres, 4 Vesta, 2 Pallas, and 10 Hygiea, account for half of the belt's total mass, with almost 1/3 accounted for by Ceres alone. Composition. The current belt consists primarily of 3 categories of asteroid: C-type, or carbonaceous asteroids, S-type, or silicate asteroids, and M-type, or metallic asteroids. Carbonaceous asteroids, as their name suggests, are carbon-rich and dominate the belt's outer regions. Together they comprise over 75% of the visible asteroids. They are more red in hue than the other asteroids and have a very low albedo. Their surface composition is similar to carbonaceous crondite meteorites. Chemically, their spectra match the primordial composition of the early solar system, with only the lighter elements and volatiles removed. S-type, silicate-rich asteroids are more common toward the inner region of the belt, within 2.5 AU of the Sun. The spectra of their surfaces reveal the presence of silicates and some metals, but no significant carbonaceous compounds. This indicates that their materials have been significantly modified from their primordial composition, probably through melting and reformation. They have a relatively high albedo and form about 17% of the total asteroid population. M-type, metal-rich asteroids, form about 10% of the total population. Their spectra resemble that of iron-nickel. Some are believed to have formed from the metallic cores of differentiated progenitor bodies that were disrupted through collision. However, there are some silicate compounds that can produce a similar appearance. For example, the large M-type asteroid, 22 Calliope, does not appear to be primarily composed of metal. Within the asteroid belt, the number distribution of M-type asteroids peaks at a semi-major axis of about 2.7 AU. It is not yet clear whether all M-types are compositionally similar, or whether it is a label for several varieties which do not fit neatly into the main C and S classes. One mystery of the asteroid belt is the relative rarity of V-type, or basaltic asteroids. Theories of asteroid formation predict that objects the size of Vesta or larger should form crusts and mantles, which should be composed mainly of basaltic rock, resulting in more than half of all asteroids being composed either of basalt or olivine. Observations, however, suggest that 99% of the predicted basaltic material is missing. Until 2001, most basaltic bodies discovered in the asteroid belt were believed to originate from the asteroid Vesta, hence their name, V-type. However, the discovery of asteroid 1459 Magnia revealed a slightly different chemical composition from the other basaltic asteroids discovered until then, suggesting a different origin. The hypothesis was reinforced by the further discovery in 2007 of two asteroids in the outer belt, 7472 Kamakiri and 1991 RY16, with differing basaltic composition that could not have originated from Vesta. These latter two are the only V-type asteroids discovered in the outer belt to date. The temperature of the asteroid belt varies with distance from the Sun. For dust particles within the belt, typical temperatures range from 200 Kelvin (-73 Celsius) at 2.2 AU down to 165 Kelvin (-108 Celsius) at 3.2 AU. However, due to rotation, the surface temperature of an asteroid can vary considerably as the sides are alternately exposed to solar radiation and then to the stellar background. Main belt comets. Several otherwise unremarkable bodies in the outer belt show cometary activity. Since their orbits cannot be explained through the capture of classical comets, it is thought that many of the outer asteroids may be icy, with the ice occasionally exposed to sublimation through small impacts. Main belt comets may have been a major source of the Earth's oceans, since the deuterium-hydrogen ratio is too low for classic comets to have been the principal source. Orbits. Most asteroids within the asteroid belt have orbital eccentricities of less than 0.4 and an inclination of less than 30 degrees. The orbital distribution of the asteroids reaches a maximum at an eccentricity of around 0.07 and an inclination below 4 degrees. Thus, while a typical asteroid has a relatively circular orbit and lies near the plane of the ecliptic, some asteroid orbits are highly eccentric or travel well outside the ecliptic plane. Sometimes the term main belt is used to refer only to the more compact core region where the greatest concentration of bodies is found. This lies between the strong 4:1 and 2:1 Kirkwood gaps at 2.06 and 3.27 AU, and at orbital eccentricities less than roughly 0.33, along with orbital inclinations below 20 degrees. The core region contains approximately 93.4% of all numbered minor planets within the solar system. Kirkwood gaps. The semi-major axis of an asteroid is used to describe the dimensions of its orbit around the Sun, and its value determines the minor planet's orbital period. In 1866, Daniel Kirkwood announced the discovery of gaps in the distances of these bodies' orbits from the Sun. They were located at positions where their period of revolution around the Sun was an integer fraction of Jupiter's orbital period. Kirkwood proposed that the gravitational perturbations of the planet led to the removal of asteroids from these orbits. When the mean orbital period of an asteroid is an integer fraction of the orbital period of Jupiter, a mean motion resonance with the gas giant is created that is sufficient to perturb an asteroid to new orbital elements. Asteroids that become located in the gap orbits, either primordially because of the migration of Jupiter's orbit or due to perturbations or collisions, are gradually nudged into different, random orbits with a larger or smaller semi-major axis. The gaps are not seen in a simple snapshot of the locations of the asteroids at any one time, because asteroid orbits are elliptical, and many asteroids still cross through the radii corresponding to the gaps. The actual spatial density of asteroids in these gaps does not differ significantly from the neighboring regions. The main gaps occur at 3:1, 5:2, 7:3, and 2:1 mean motion resonances with Jupiter. An asteroid in the 3:1 Kirkwood gap would orbit the Sun 3 times for each Jovian orbit, for instance. Weaker resonances occur at other semi-major axis values, with fewer asteroids found than nearby. For example, an 8.3 resonance for asteroids with a semi-major axis of 2.71 AU. The main or core population of the asteroid belt is sometimes divided into 3 zones, based on the most prominent Kirkwood gaps. Zone 1 lies between the 4:1 resonance, 2.06 AU, and 3:1 resonance, 2.5 AU, Kirkwood gaps. Zone 2 continues from the end of Zone 1 out to the 5:2 resonance gap, 2.82 AU. Zone 3 extends from the outer edge of Zone 2 to the 2:1 resonance gap, 3.28 AU. The asteroid belt may also be divided into the inner and outer belts, with the inner belt formed by asteroids orbiting nearer to Mars than the 3:1 Kirkwood gap, 2.5 AU, and the outer belt formed by those asteroids closer to Jupiter's orbit. Some authors subdivide the inner and outer belts at the 2:1 resonance gap, 3.3 AU, while others suggest inner, middle, and outer belts. Collisions. The high population of the asteroid belt makes for a very active environment, where collisions between asteroids occur frequently, on astronomical timescales. Collisions between main belt bodies with a mean radius of 10 kilometers are expected to occur once every 10 million years. A collision may fragment an asteroid into numerous smaller pieces, leading to the formation of a new asteroid family. Conversely, collisions that occur at low relative speeds may also join 2 asteroids. After more than 4 billion years of such processes, the members of the asteroid belt now bear little resemblance to the original population. Along with the asteroid bodies, the asteroid belt contains bands of dust with particle radii up to a few hundred micrometers. This fine material is produced, at least in part, from collisions between asteroids and by the impact of micrometeorites upon the asteroids. Due to the Ponting-Robertson effect, the pressure of solar radiation causes this dust to slowly spiral inward toward the Sun. The combination of this fine asteroid dust, as well as ejected cometary material, produces the zodiacal light. This faint auroral glow can be viewed at night, extending from the direction of the Sun along the plane of the ecliptic. Particles that produce the visible zodiacal light average about 40 UM in radius. The typical lifetimes of such particles are about 700,000 years. Thus, to maintain the bands of dust, new particles must be steadily being produced within the asteroid belt. Meteorites. Some of the debris from collision can form meteorites that enter the Earth's atmosphere. Of the 50,000 meteorites found on Earth to date, 99.8% are believed to have originated in the asteroid belt. A September 2007 study by a joint US-Czech team has suggested that a large body collision undergone by the asteroid 298 Baptistina sent a number of fragments into the inner solar system. The impacts of these fragments are believed to have created both Tycho crater on the Moon and the Chicxulub crater in Mexico, the relict of the massive impact which is believed to have triggered the extinction of the dinosaurs 65 million years ago. Families and groups. In 1918, the Japanese astronomer Kitsuga Hirayama noticed that the orbits of some of the asteroids had similar parameters, forming families or groups. Approximately 1/3 of the asteroids in the asteroid belt are members of an asteroid family. These share similar orbital elements, such as semi-major axes, eccentricity, and orbital inclination, as well as similar spectral features, all of which indicate a common origin in the breakup of a larger body. Graphical displays of these elements, for members of the asteroid belt, show concentrations indicating the presence of an asteroid family. There are about 20 to 30 associations that are almost certainly asteroid families. Additional groupings have been found that are less certain. Asteroid families can be confirmed when the members display common spectral features. Smaller associations of asteroids are called groups or clusters. Some of the most prominent families in the asteroid belt, in order of increasing semi-major axes, are the Flora, Eunomia, Coronis, Eos, and Themis families. The Flora family, one of the largest with more than 800 known members, may have formed from a collision less than 1 billion years ago. The largest asteroid to be a true member of the family, as opposed to an interloper, in the case of Ceres with the Geophion family, is 4 Vesta. The Vesta family is believed to have formed as the result of a crater-forming impact on Vesta. Likewise, the HED meteorites may also have originated from Vesta as a result of the collision. 3 prominent bands of dust have been found within the asteroid belt. These have similar orbital inclinations as the Eos, Coronis, and Themis asteroid families, and so are possibly associated with these groupings. Periphery. Skirting the inner edge of the belt, ranging from 1.78 and 2 AU, with a mean semi-major axis of 1.9 AU, is the Hungaria family of minor planets. They are named after their main member, 434 Hungaria. The group contains at least 52 named asteroids. The Hungaria group is separated from the main body by the 4:1 Kirkwood gap, and their orbits have a high inclination. Some members belong to the Mars-crossing category of asteroids, and gravitational perturbations by Mars are likely a factor in reducing the total population of this group. Another high-inclination group in the inner part of the asteroid belt is the Phocea family. These are comprised primarily of S-type asteroids, whereas the neighboring Hungaria family includes some E-types. The Phocea family orbit between 2.25 and 2.5 AU from the Sun. Skirting the outer edge of the asteroid belt is the Cybele group, orbiting between 3.3 and 3.5 AU. These have a 7:4 orbital resonance with Jupiter. The Hilda family orbit between 3.5 and 4.2 AU and have relatively circular orbits and a stable 3:2 orbital resonance with Jupiter. There are few asteroids beyond 4.2 AU until Jupiter's orbit. Here the 2 families of Trojan asteroids can be found, which, at least for objects larger than 1 kilometer, are approximately as numerous as the asteroids of the asteroid belt. New families. Some asteroid families have formed recently in astronomical terms. The Charon cluster apparently formed about 5.7 million years ago from a collision with a 33-kilometer radius progenitor asteroid. The Veritas family formed about 8.3 million years ago. Evidence includes interplanetary dust recovered from the ocean sediment. More recently, the Tatura cluster appears to have formed about 450,000 years ago from a collision with a main belt asteroid. The age estimate is based on the probability of the members having their current orbits rather than from any physical evidence. However, this cluster may have been a source for some zodiacal dust material. Other recent cluster formations, such as the Nannini cluster, circa 1 to 5 million years ago, may have provided additional sources of this asteroid dust. Exploration. The first spacecraft to traverse the asteroid belt was Pioneer 10, which entered the region on July 16, 1972. At the time, there was some concern that the debris in the belt would pose a hazard to the spacecraft, but it has since been safely traversed by 11 Earth-based craft without incident. Pioneer 11, Voyagers 1 and 2, and Ulysses passed through the belt without imaging any asteroids. Galileo imaged the asteroid 951 Gaspra in 1991 and 243 Ida in 1993. NEA imaged 253 Mathilde in 1997, Cassini imaged 2685 Masursky in 2000, Stardust imaged 5535 Anne Frank in 2002, New Horizons imaged 132524 APL in 2006, Rosetta imaged 2867 Steins in 2008, and Dawn has been orbiting Vesta since July 2011. Due to the low density of materials within the belt, the odds of a probe running into an asteroid are now estimated at less than 1 in a billion. All spacecraft images of belt asteroids to date have come from brief flyby opportunities by probes headed for other targets. Only the NEA and Hayabusa missions have studied asteroids for a projected period in orbit and at the surface, and these were near-Earth asteroids. However, the Dawn mission has been dispatched to explore Vesta and Ceres in the asteroid belt. If the probe is still operational after examining these two large bodies, an extended mission is possible that could allow additional exploration, possibly of Pallas.